Hello and welcome to this short presentation on statistics looking at central tendencies. This is a recap presentation, so it does assume you understand some basic concepts such as the mean, mode, medians, and you've been introduced to a standard deviation. And here's an overview of the contents of the presentation. The left hand side of the table here shows the various sections contained within the presentation, and the right hand side shows the approximate start times to hopefully aid your ease of access through the presentation. But please note all times are generally rounded to the nearest minute. Statistics is the science of collecting, classifying, analysing and ultimately using numerical data. It's extensively used by government departments, advertisers, scientists and of course engineers in order to obtain information and to display information. A statistic must be representative of the distribution of data being considered. Statistics used are near the centre, in other words, measures of central tendency or central location, often called averages. The most common averages are the mean, the mode, and the median, and we'll be looking at all three of those in this presentation. Firstly, the arithmetic mean, or sometimes simply called the mean, denoted by the symbol x bar. The arithmetic mean, x bar, the average, of a set of values is the sum of the values divided by their number or their frequency. In terms of notation, sometimes written as x bar, the mean is equal to the summation of the frequencies times the values of the series, all divided by the summation of the frequency. So it's a complicated formula, but it's quite simple in practice. So the summation, the symbol sigma, means summate up the f times x's, frequency times the values or the scores in this case you'll see below. So it's called the sum of the products of f times x. And the summation of f is simply the sum of the frequencies or the total number of values in the set being considered. So consider example 1 here. We've got to calculate the mean score of the following data. So we've got the score, which is denoted as x here. Scores go from 1, 2, 3, 4, 5 through to 6. Those are our score categories, and the frequency of each of the categories or each of the score f. We've got 5 for the first score of 1, so the score of 1 occurred 5 times in this survey, the score of 2 occurred 8 times, score of 3 16 times, score of 4 15 times, score of 5 9 times, and score of 6 7 times. What we're going to do now is work out the x bar, the arithmetic mean for this series. So using our formula, summation of f times x, all divided by the summation of f. We can write also, just for your reference, that could be summation of x times f over summation of f. It doesn't really matter whether we multiply by the f first or the x first. So looking at the top line of this equation, for the first category, the score of 1, it occurred 5 times. So we will have 1 times 5. We're actually doing there x times f, but it doesn't really matter. Looking at the next category, we're going to add to that the score of 2 times 8. So 2 occurred 8 times. Then we're going to add to that the next category. A score of 3 occurred 16 times. So that would be 3 times 16. Add to that the next category. 4 occurred 15 times. So 4 times 15. And looking at the last categories, I've got 5 occurred 9 times. Plus the 6 occurred 7 times. That's all divided by the summation of the frequencies, simply adding up the frequencies, 5 plus the 8 plus the 16 plus the 15 plus the 9 plus the 7. So doing the numbers on this, on top line 216 when you apply your BODMAS to the top line, and on the bottom line adding up the frequencies we get 60. Doing the sum on that, 3.6. So 3.6 is the mean average score for that set of data. Exercise 1 here. Exercise is related to calculating the arithmetic mean. We've got 5 machine bars. The turn bars here are measured and their diameters in millimeters were found to be 16.083 millimeters, 16.02 millimeters, 16.02 millimeters, 16 and 16.03 millimeters. We've got to find their mean diameter. So from our formula, the x bar is equal to the summation of the fx divided by the summation of the f's. So in this case, looking at our series, we've got 2 diameters of 16.03 in our listing above, and we've got plus 2 diameters of 16.02, again looking at the listing above, plus finally 1 times a 16mm diameter. That's all divided by the summation of the frequencies, which would be 5. So doing the numbers on this, the top line becomes 80.1 divided by 5. So the mean diameter in this particular case is 16.02 millimeters. Exercise 2 here, we've got the diameters of 8 pipes being measured, and we've got a list of the 8 pipes here in the question. We've got to calculate the mean diameter of the pipes. So again, looking at our series, there's only 2 diameters that are the same, and that's the 108.98. We've got 108.98, 108.98. I've just put them in ascending order here, that's all, so we can clearly see that. But all the other ones occur only once. So calculating my mean, my x bar here, I will simply apply the formula we're using, summation of the fx's divided by summation of the f's. So on the top line, we will get the 108.91 plus 2 times 108.98, because there's 2 of those, but all the other terms are all the individual values, so there's just one of those. So working out the top line, in this case will give me 872.76, and of course there are 8 pipes in the series, so we divide that by 8. So the mean average diameter for these 8 pipes is 109.095 millimeters. Exercise 3 here, we're given that 22 large bricks have a mean mass of 24 kilograms, and then 18 similar bricks have a mean mass of 23.7 kilograms. We've got to find the mean mass for 40 bricks. When we add all the bricks together, we get 40 there. So in this case, to work out the x bar, back to our formula again, we've got 22 is the frequency, the f, and that's multiplied by the mass of the 22 large bricks, which is 24 we're given in the question, and we add to that 18 is the frequency of the, they're called similar bricks here, that have a mass of 23.7 kilograms. That's all divided by the 22 plus the 18, a number of bricks. So doing numbers on this, the x bar in this case is 954.6 divided by the total number of bricks, which was 40. Gives us an average value of 23.865 kilograms. Exercise 4 is asking us to work out the mean, but this time of grouped data. So what we have here is resistance in categories of 110 to 112 ohms, 113 to 115 ohms, 116 to 118 ohms, 119 to 121 ohms, and 122 to 124 ohms. And we've got the frequency for each of the categories. So there are 2 resistors that fitted in the 110 to 112 ohm category. There were 8 resistors that fitted in the 113 to 115 ohm category, and so on. So to work out the x bar here of this grouped data, what we're going to do is take the mean value of each of the categories. So in other words, go into our formula, summation of fx over summation of f, our standard formula here. I've got the mean category value of 111 times the frequency of 2. Okay, so 111 is the average of 110, 112. And I add to that the mean value of the next category, which would be 114 times by its frequency, which is 8. The next category, the mean value is 117. So the average, if you like, 116 plus 118 divided by 2 there gives me the 117, and that's multiplied by its frequency. Final category is the mean value is 120, and that's times by the frequency of 9, plus 123, and that's times the frequency of 3. That's all divided by the summation of the frequencies. So doing the numbers on this, the top line, get 4,338 divided by the bottom line there of 37 items in this listing. That gives us the mean resistance of 117.2 ohms. The next central tendency we're going to look at is called the median. Now we need to be careful with the median because it depends on whether it's an odd or an even data set as to how we apply it. So let's first of all look at the median of an odd set of numbers. The first thing we must always do with the median is to put our numbers in the ascending or descending order of size. That's the first thing you must do. They're not always given in that way in the question, but we must do that. Once you've done that, the median is simply the value halfway along the data set. So for example, in this example 2 here, we've got an odd set of data here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 items of data. That means the middle term will be the 5th term in the series. So when the values are in ascending order, which they are here, then it's the middle term will be the median. We've got 4 numbers to the left of it and 4 numbers to the right of it. We don't care about their magnitudes. It's just that we got the symmetry of the data set there. So for an odd set of data, it's simply the middle term in the series gives you the median. So the median in this case is 6. When I'm looking at the median for an even set of data, we need to be a little bit more careful. We still need to arrange the numbers in ascending or descending order of size. We still need to do that. But with an even set of data, there are actually 2 numbers in the middle. So example 3 here, we're given an even set of data. We've got 8 items in the data, 1, 2, 3, 4, 5, 6, 7, 8. So what we find is we have 2 numbers in the middle of the series. What we do to find the median of an even set of data, we average those 2 middle numbers. So 7 plus 9 divided by 2 will give me 8. So the median in this case is the average of the 2 middle numbers, and that's the value of 8. Example 4. Example 4 is going to ask us to find the median value of grouped frequency distribution. So what we've got here is the resistance. Again, we've got our categories here, 110, 112, 113, 115, so it goes on. We've got the frequency for each of the categories. So we've got 2 in the first category, 8 items in the second category, 15 in the third, and so on. And what I've done here is added another row called cumulative frequency. And this is where I add up the frequencies. We looked at this in the previous presentation on data collection and presentation. So in this case, in the first category, I got a frequency of 2. In the second category, I got a frequency of 8, but cumulative frequency would now be 10, the 2 plus the 8. For the next category, the frequency is 15, but the cumulative frequency will be 25. In other words, the 10 plus the 15. Next category, I've got a frequency of 9, but adding that to the 25, that gives me a running total, if you like, cumulative frequency of 34. And the final category, the frequency was 3. Adding that to my cumulative frequency, I get 37. There are 37 items in this batch. So noting the total frequency in this case is 37. This is an odd number of data. So there will be a middle term in the series, one middle term in the series. Thus, to find the midpoint, we divide the 37, the total number of items, by 2, which gives 18.5, and rounding that up, the median will be the 19th term in the series. Now we find this very easily from the cumulative frequency row above. So from the cumulative frequency tally, it is seen that a 19th term occurs in the 116 to 118 ohm category. In other words, looking at the categories here, up to 10 is occurring into the second category, up to 25 occurs into the third category. So when we're looking at 19th term, it must occur in the third category. It's not in the second category because that goes up to 10 items. But we've got the 19th item. But the third category goes up to 25, so the 19th item must be in the third category. So in this case, the medium category is specified as 116 to 118 ohm category. Exercise 5. We're given the hourly wages of 5 employees in an office are £3.04, £5.92, £4.56, £16.40 and £5.50. We're asked to calculate the median and the mean in this case. So calculating the median, don't forget to find the median, we have to put our data set in either ascending or descending order. I put mine in ascending order in this particular case, so I've got the £3.04, the £4.56, £5.50, £5.92 and £16.40. The median is the middle term of a series of data, and as this is an odd set of data with 5 items in it, the middle term is clearly seen is £5.50. So the median is £5.50. To calculate the mean, using our formula of x bar is equal to summation of fx over summation of f. In this case, I basically add up the 5 wages because they're all different here. So I simply add them up on the top line, divide by the number of them, 5. Doing the numbers on this, it gives me a mean value of £7.08. You'll notice that the mean value is significantly higher than the median value for these data. Later on, we'll look at reasons why that can be. Okay, exercise 6 here, we're asked to calculate the median score of the following 60 scores. Again, we've got a category here denoted as X, scores of 1, 2, etc. up to 6. And we've got the frequencies F, so the score of 1 occurred 5 times, the score of 2 occurred 8 times, etc. So what we're going to do here is calculate the median, but we're going to use the cumulative frequency to do this. I just denoted this as summation of F here. So looking at the frequencies, for the first category, we've got a frequency of 5, so the cumulative frequency starts off at 5. Looking at the second category, we've got a frequency of 8, so the cumulative frequency is 5 plus 8, it gives me 13. Looking at the third category, the frequency was 16, so the cumulative frequency is 13 plus 16 is 29. Fourth category, frequency is 15, so the cumulative frequency is 29 plus the 15 is 44. Fifth category, frequency is 9, so the cumulative frequency is 53. And then finally, the final category, the category 6, the frequency is 7, so the total frequencies now is 60. So noting that 60 is even set of data. So now it means the median will be the average of two middle terms. So what are those middle terms? Well, 60 divided by 2 will give me 30. So it would be the 30 and the 31st term in the series that we need to consider. Now again, this is very easy. Once you've got the cumulative frequency tally, it's very easy to find where these occur. So in category 3, for example, it says up to 29 items occur up to category 3, and up to category 4, the score of 4, 44 items. So we can quite clearly see that the 30th and the 31st terms will occur in the category 4 there, where the score is 4. So the median in this case is simply stated as 4. Again, I emphasize the use of the cumulative frequency row there makes it very easy to find where the median values occur in this case. Exercise 7 here, we've got some group data here related to voltages in electrical circuits. So we've got the volt categories here, so 47 to 48 volts, we had a frequency of 1, there's one item in that range. 48 to 49 volts, frequency of 5, 49 to 50 volts, frequency of 9, and so it goes on. We've got to find the median voltage here. So again, I'm going to use the cumulative frequency values in this particular case. So starting off in the first category, the 47 to 48 volts, we've got one item, so the cumulative frequency is 1. In the 48 to 49 category, the frequency is 5, so that gives me 1 plus 5 is 6 in the cumulative frequency row. Next category, 49 to 50 volts, the frequency was 9, so 9 plus 16 gives me 15 in the cumulative frequency row. I'll let you review the rest of the row there up to the 100 voltages that we've got in our table. So note, the total frequency is 100, again is even number data set, so there will be two items in the middle of our series when it's arranged in ascending order. So the midpoint in this particular case is 50, so 50 and the 51st term of the series will be the median values we're looking for. From the cumulative frequency tally, we can clearly see the 50th and the 51st term will occur in the 51 volts to 52 volt category. Again, going back to our categories, in this category it's saying up to 32 items occur in the 50 to the 51st range, so up to that level the 32 items, but up to the 51 to 52 volt range 70 items occur there, so we can clearly see our 50th and our 51st term are in that category. So the median category is simply specified as 51 to 52 volts. And the final central tendency we're going to look at is the mode, and probably the easiest of all to determine. The mode of a set of numbers is simply the number that occurs the most often, the most frequent. In example 4, looking at these series of numbers here, and I've arranged them in ascending order here for convenience, we can clearly see that the number 4 occurs the most. It occurs 3 times. All the other numbers occur less than that. So the mode is simply 4. This is actually called a unimodal set of data because there's only one mode in the set. We can have a situation where we have no mode. Example 5 shows us this. We've got a set of numbers here, and you can see in this set no one number occurs more than any other number. They only occur once. So this set of data has no mode. And we can have a bimodal situation. Example 6 shows this. We've got a set of numbers here, and they're arranged in ascending order again for convenience, and we can clearly see that the number 5 occurs 3 times and the number 8 occurs 3 times in this particular set of data. So there are 2 modes here because the 5 and the 8 occur the most. Exercise 8 here wants us to find the mode of the following numbers. They're not in ascending order. They don't really have to be for the mode, but it's more convenient to analyse them if they are. So below I put them in ascending order, and when you do, you can clearly see that 5 occurs the most. It occurs 3 times. So in this case 5 is the mode. Exercise 9 here relates to a group frequency, group data we've got here. We've got to find the mode again, given resistances, and they're in categories: 110, 112, 113, 115, 116, 118, and so on. And we've got the frequencies for each of the categories underneath it. And simply by inspection, by looking at the data given to us, the mode is going to be the 116, 118 category, as it's got the largest frequency. Let's have a little discussion now about the mean, the mode, and the median, and when to specify an average. So when do you specify the mean, the median, or the mode? It depends on the applications, as you'll see later. The arithmetic mean. This is the most common average used in statistical work, particularly in engineering and manufacturing, looking at production rates and tolerances of components off production lines. It's very useful in those kind of instances. It wouldn't be so useful though if we were trying to find the average screw size that's used in a workshop, because if we did work out the average screw size, that probably wouldn't relate to the actual stock sizes of screw. So we probably want more like the mode we use in that particular instance. But generally speaking, in engineering, most data is continuous, and the arithmetic mean is very useful. However, the mean can be misleading, especially if it has very extreme values in the series. Just take these numbers here, say their hourly rates, for example. We've got a £9, a £10, £11, £12, and £100. When you work out the mean average using our formula, you add up all the values and divide by the number of them. You get a value of £28.40. Now we're going to compare that in a moment to the median below, and you'll see why the mean has been affected by extreme values. Let's look at the median. The median is simply the halfway value along a series of numbers. It's quite simple to find. Not so often used in scientific work, but it doesn't get affected by extreme values as the median does. This is shown here. If we take the same set of numbers used above, the £9, £10, £11, £12 and £100, the median is simply the middle term of that series. So it's simply the £11. So in other words, when you compare the median to the mean value above, you can see how it didn't get affected by that extreme value of £100 per hour, whereas the mean did. The mean shows the average is 28.4, which is not really representative of the data there, when most people are earning well below that value. Finally, the mode. The mode is the most popular item in a series of data, quite simple to evaluate and very useful for stock taking or stock control purposes. Exercise 10 here, we're asked to state which of the 3 averages, the mean, the mode, or the median, would be preferable in the following different contexts. So A storekeeper required to keep a minimum stock of bolts that are commonly used in the workshop. B, an employer monitoring production of the works, production line. And C, a union wage negotiator involved with discussion with management over pay rises. Exercise 10 solutions here. I'll let you read them and consider them for yourself. What we're going to look at now are measures of dispersion. That's a very fancy way of saying the spread of the numbers or spread of the data. Exercise 1D tries to illustrate this. So in part A, we're asked to calculate the arithmetic mean of the numbers 14, 15 and 16. To do that, we simply add them up and divide by the number of them. Adding them up, 14 plus 15 plus 16 divided by 3 gives you a mean average of 15. In part B, we're asked to find the arithmetic mean of the numbers 33, 2 and 10. If we add 33 to 2 to 10, we again get 45 divided by 3, because of 3 numbers, that again gives us a value of 15. So the mean average is 15. For reference, here are the calculations for the mean. So what can be said about the mean values quoted above? Well, the data that were given in both cases both have an arithmetic value of 15, but the spread of the data is considerably different. In the first instance, in part A, the spread of the data is very close to 15. We've got a 14 and a 16 just either side of the 15. But in part B, the spread of the data is much larger. Numbers of 33 and 2 are well away from the average of 15. So in other words, the mean average tells us nothing about the spread of the data. So we need to look at other ways of defining the spread of the data. Okay, the first method of dispersion we're going to use is the range. The range is simply the largest value in our data set, take away the smallest value. Look at example 7. We've got 8 students going to sit a maths test, and their marks were, out of 10, 2, 6, 6, 7, 7, 7, 8 and 9. We're asked to find the average mark and the range. So the average is simply working out the frequencies times the scores in this case. So 2 plus 2 times 6 plus 3 times 7 plus an 8 plus a 9. That totals 52. There are 8 people sitting this test. So the average score would be 52 divided by 8 would be 6.5. If we want the range, the spread of the data, it's simply the largest value, the maximum score in this case, which was 9, take away the smallest value, the minimum score, which was 2. So the range of the data is 7. So now we can define this data set as having a mean of 6.5 and a range of 7. Another method of dispersion we can use is the standard deviation, denoted often by the lowercase sigma, that sideways looking 6 symbol. This is a preferable method of assessing dispersion within engineering problems. So mathematically, the standard deviation is given by what looks like a very complicated formula. It's the square root of the summation of open bracket, the frequencies times by, in brackets, x take away the x bar, all squared, and that's all divided by the summation of the frequency. So it looks like a very complicated formula here, given without proof here. There is a proof behind this. We're going to solve this using a tabulated method, and that's shown over leaf. Okay, example 8 here. We're asked to find the standard deviation for a set of numbers that's given in this particular example there. We're going to use a tabular approach to solve this problem. We're using the formula that we saw on the previous slide, just repeated here for convenience. You might find that some scientific calculators have built-in functions for calculating standard deviation. So using our tabulated method, on the left-hand side here, I've got my x and my frequency values from the question given. So looking at the question given, I've just written these in ascending order here. I've got the value of 10 that occurs once, the value of 12 occurs once, the value of 16 occurs once. The value of 20, if we look at the list of figures above, occurs 3 times in that list. The value of 22 occurs once, 24 occurs twice in the list, and 32 occurs once. If I add up the frequencies here, so summate the frequencies, I get a value of 10. There are 10 numbers in the series, that's correct. And if I do my product of the f times the x, the frequency times the x value, the value of the number in this case, I can fill in this column. So f times x here, this would be 10 times 1, be 12 times 1, 16 times 1. This would be 20 times 3, because the frequency is 3 here, so that would give me 60. And 22 times 1, 24 times 2, frequency is 2 for the value 24, and then 32 times 1. If I summate the fx values, I get 200, and we know from previous work to find the arithmetic mean, the x bar, it's the summation of the fx divided by summation of the f. So in this case, the mean value is 20. So what I've got now basically is this value of the equation. What I'm going to do now in the next 3 columns is work out the rest of the equation, again using this tabular format. So in the next column here, I've got x take away x bar. So x is in the left-hand column. So in this particular case, for the first row, I would have 10 as my x, and I take away my x bar, which is 20. So that gives me minus 10. The next row, I've got 12 as my x, and I take away 20 from my x bar, so I get minus 8. 16, take away 20, gives me minus 4. And for the next row, where the x value is 20, so 20 take away x bar, which is 20, gives me 0. And I've got 22 as an x, take away 20 for the x bar, gives me positive 2. 24 take away 20 gives me positive 4. And 32 take away the x bar of 20 gives me 12. In the next column, what I'm doing is simply squaring the previous column. So x take away x bar all squared. Now don't forget, when you square a negative number, it becomes positive. So in all this column here, all the numbers should be positive. So negative 10 squared gives me positive 100, negative 8 gives me positive 64, and negative 4 is positive 16. Obviously 0 squared is still 0, 2 squared is 4, 4 squared is 16, and 12 squared is 144. The final column in the tabulation is f, the frequency, now times the x take away x bar all square. So in other words, it's the f column here on the left hand side there multiplied by this column here. So 1, the f for the first row is 1. So 1 times the 100 is 100. 1 times 64 is 64. 1 times 16 is 16. We've got 3 times 0 here, but of course that's 0. We get 1 times the 4 is the 4. We get 2 times 16. Frequency is 2 for this row. So 2 times 16 is 32. And then 1 times 144 is 144. Now summate that column, and that gives us 360. So what we've basically done with this tabular approach is now to work out that top line. This top line here is actually the last column in the table. This column here is the top line. We've already got the bottom line, the summation of f. We've already calculated that. That's up here in this column. So now dividing the top line by the bottom, so 360 divided by 10, and then square rooting. Don't forget, we've got to square root the entire function here. Square rooting, we get plus or minus 6. Don't forget, when you take a square root, there are always two answers, a plus and a minus answer. So 360 divided by 10 is 36, and the square root of 36 is plus or minus 6. Note for reference that the value of the standard deviation sigma is the root mean squared value of the distance of members of a set from the mean value, denoted as x bar. Being a distance, standard deviation sigma cannot have a negative value. However, since the final step in determining a standard deviation is extracting the square root, as shown here in this formula, positive and negative answers always result. Whenever we take a square root, we always have a positive and negative solution. When a positive value only is stated for the standard deviation, this is strictly correct. However, the positive and negative values may be stated and should be interpreted as a distance either to the left, negative, or the right, positive, of the mean, the x bar value. Reference note continued. The positive and negative should be considered essentially as a plus or minus either side of the arithmetic mean, the x bar, on a normal distribution curve. It should be noted that engineers are often interested in plus or minus 3 standard deviations from the arithmetic mean, in other words, a dispersion of x bar plus or minus 3 standard deviations, as shown in the diagram of the normal distribution curve below. So here's our x bar mean, and here are the plus 3 standard deviations to the right of the x bar, and the minus 3 standard deviations to the left of the x bar. Within manufacturing processes, we've often heard the term 6 sigma used, and that relates to the data under a normal distribution curve between plus or minus 3 standard deviations. As a numerical illustration, if the standard deviation sigma was 6 millimeters, then the dispersion, the spread of the data related to a normal distribution curve would be x bar plus or minus 3 sigma. So in this case that would be x bar plus or minus 18 millimeters. So although within this presentation I'd often do state the standard deviation as a positive and negative value, because we are taking a square root for the final answer, in theory the standard deviation is purely a positive value. Example 8 continued here. So summarising the previous slide, our arithmetic mean, our x bar, is 20. Our standard deviation, our sigma, is 6. Now in engineering problems, we're often interested in a plus or minus 3 standard deviations. We'll look at this in more detail on the following slides, but for the moment just accept that. So we want to find the spread of the data as far as plus or minus 3 standard deviations are concerned. So that's from the mean. So the mean in this case, the x bar, is 20 from above. And we're going to plus or minus from that 3 times 6, 3 times standard deviation, so that's 18. So the spread of the data from the plus or minus 3 standard deviations would actually be 20 take away 18, give me 2, to 20 plus 18 would give me 38. So using our plus or minus 3 standard deviations, the spread of the data would follow 2 right the way through to 38 in this particular case. If we go back to the range of the data, that would simply be the largest value take away the smallest value, and if we look at the data, that will be 32 take away 10. So the range would be 22. Okay, exercise 1S here. We're given a sample of snap links from a chain that was tested to destruction, and the force that caused the failure was recorded in the table below. So in the first row we have the force in kilonewtons, and then we have the frequency, the number of items that failed in the category stated. And notice the way the categories are listed here. In the first category we've got 47 to less than 48 kilonewtons, one item failed in that category. 48 to less than 49 kilonewtons, 5 items failed. 49 to less than 50 kilonewtons, 9 items failed, and so it goes on. When you come to do the calculation on this, make sure you take the midpoint of each of those categories. So for the first one it would be 47.5, for the second 48.5, then 49.5, and so on. What you've got to do is work out the mean and the standard deviation of the force causing the failure, and use the tabular approach shown in the previous slide. The answers are given here for your reference. The mean is 51.4 kilonewtons and the standard deviation is 1.4 kilonewtons. That's one standard deviation. I should just say as an observation here that the force values given there are in histogram format. In other words, they're continuous data. What you've got here are categories of 47 to less than 48 kilonewtons, the first category, and then the second category got 48 to less than 49. So that's continuous right the way from 47 through to less than 49. In the next category you've got 49 to less than 50, so that continues the pattern onward. So this is continuous data from the left hand side, 47 kilonewtons, to the right hand side at less than 56 kilonewtons. And that's just for reference. Okay, I'm very briefly going to talk about the normal distribution here. I'm not going to get heavily into this, it's just an overview. I'm not going to do any particular calculations on this, that's for a later presentation. But I'm just going to outline what a normal distribution is and how it relates to the standard deviation. If the distribution is large and is reasonably symmetrical, it's illustrated by a normal distribution curve. The figure 1 here, a normal distribution, shows us a bell-shaped curve where almost 99.5% of the population is encompassed within plus or minus 3 standard deviations of the mean, the x bar value. So the mean is here, the x bar value would be here on this line here, and within plus or minus 3 standard deviations, so going 1, 2, 3 to the left and 1, 2, 3 standard deviations to the right, we would encompass 99.5% of our population. That's what the normal distribution assumes. Notice we've got frequency plotted on the vertical and the variate on the horizontal. So the characteristics shown here can be used to determine if the data supplied conforms to a normal distribution. In figure 2 here on the right hand side, we show a normal distribution curve. We have the frequency plotted on the vertical axis and the variate plotted on the horizontal axis. Here's our mean average value, x bar, the center of the curve. And the curve is symmetrical either side of the x bar. And on the horizontal axis we show 3 standard deviations to the right of the x bar and 3 standard deviations to the left of the x bar. And the dispersion, or the range associated with the plus or minus 3 standard deviations, should encompass all of our data. If we now apply this check to exercise 1s outlined on the previous slide, we can calculate the dispersion for the sample in that exercise. So x bar plus or minus 3 standard deviations. Well, the x bar was 51.4 kilonewtons from the answer in the question. Then we add or subtract 3 times the standard deviation of 1.4 kilonewtons. Again, that was given in the answers to exercise 1s. So the range is going to be 51.4 plus or minus 3 times 1.4. So that's plus or minus 4.2 kilonewtons. So the values associated with the data of exercise 1s should lie within the range from an upper value of 55.6 kilonewtons to the lower value of 47.2 kilonewtons. I've added these values here to the normal distribution curve. Here's exercise 1s repeated for convenience. We have to calculate the mean value stated here and the standard deviation stated here for our forces. And from the data given, we can clearly see that the force values range from 47 kilonewtons through to 56 kilonewtons. So essentially our data can be considered to comply with the plus or minus 3 standard deviations. So this suggests the data conforms to a normal distribution. To check for conformity with the normal distribution, first check, does the data plot essentially a symmetrical bell shape about the x bar? The second check, does the range of data reside within plus or minus 3 standard deviations of the arithmetic mean x bar? And the third check is, are the values of the mean, the mode and the median all very similar? If we can tick boxes to all 3 checks, then there's a strong indication that our data does conform to the normal distribution. If so, we can then analyse the data in more advanced ways, considering various probabilities, and that's something we review in a later presentation, specifically related to the normal distribution. And finally, here are some skewed distributions. In the middle we have the symmetrical distribution we reviewed on the previous slide. This is the distribution where the mean, the mode and the median all have very similar values. On the left hand side here we have the positive skew of the distribution. Here the peak of the curve where the mode occurs is to the left of the median. Here is the mean to the right of the median. And on the right hand side we have a negative skew distribution. Here the peak of the curve where the mode occurs is to the right of the median and the mean is shown to the left of the median. Here are some tutorial questions on central tendencies and standard deviation. So they involve maybe the mean, the mode or the median, different questions, and also working out the standard deviation. The answers again are shown in the brackets on the right hand side. More questions on central tendencies and standard deviation problems. And the final question here on central tendencies and standard deviation. This question does involve constructing a histogram, something we looked at in a previous presentation. It suggests to use 5 classes to group the data. It wants you to work out the mean, the standard deviation and the variance of the group data. For reference, variance is simply the standard deviation value squared. And for your reference, here's the bibliography used to help generate this presentation. I hope this has been of interest to you, and thank you for viewing.